So once you have 3D distribution, you can project it onto the supergalactic plane. And here is a density landscape, high peaks corresponding to high projected density from one of the IRS-based Redshift surveys. So the big set of mountains off from center is the local supercluster. We are always in the middle, so we're sort of on the slopes of it. But why project on the supergalactic plane if you have 3D picture? And so here is the highly smoothed density distribution of galaxies in 3D from the Redshift survey. Now you see that there are really all these blobs that really are in complex relation to each other. I mentioned the second Center for Astrophysics survey by Hakra and collaborators. And what they did is they chose a slice on the sky, very thin in declination, long in right ascension, fan-shaped like that. And they did this simply in order to have manageable numbers of galaxies to observe. Went deeper than the previous survey and went past the coma cluster of galaxies. And they obtained this famous stickman diagram. The structure in the middle is the coma cluster. And it actually doesn't look like that. It is elongated in radial direction by so-called finger of God effect. Namely, remember that measured velocities of galaxies are a vector sum of the Hubble expansion velocity and a peculiar velocity the galaxy may have on its own. Now, in rich clusters of galaxies, galaxies have high velocity dispersions. They have to move fast in order to balance the gravitational potential of the dark matter. So if you look through a cluster of galaxies, suddenly some galaxies will appear to be closer to us because they're moving towards us relative to Hubble expansion. Some are moving away from us, and there'll be an elongation in what we call the redshift space as opposed to actual 3D space. So this is a two-dimensional slice through a three-dimensional structure, and you can see that galaxies actually form kind of mesh of filaments, and they're big voids. They have been noticed previous to this. Because this is a two-dimensional cut, then it's reasonable to assume that, in fact, voids must be really more of a spherical nature, or at any rate, not flat. And that sheets intersecting through this plane may actually look like filaments. In reality, they're both sheets and filaments out in large-scale structure. So there are actually two important effects about redshift space. Remember, redshift space has the radial coordinate that is associated with total measured velocity of the galaxy. And a priori, we do not know which part is due to Hubble velocity, which would be the real radial coordinate, and which part is due to peculiar motion. Statistically, we can decompose that later. Then what happens in rich clusters of galaxies, as I already mentioned, there will be an elongation towards the observer due to the radial velocity dispersion of galaxies moving fast inside the cluster. On the other hand, if we're looking not at a dense structure like a cluster, but say an intersection with one of the sheets or walls or the filaments, galaxies will be falling towards it. It's not virial structure, but it's a density excess, and so galaxies fall to it. So those which are on our side are falling towards it, acquiring velocity that makes them look like they're a little further out. Those on the other side are falling back towards that filament, and that will make them look like as if they're a little closer. So then this will squish the structure along the line of sight, the opposite of the finger of God effect. See, the dependency here is how dense or how virialized is the density that we see. In case of higher densities, like clusters of galaxies, we see the elongation, the finger of God effect. In case of low density enhancements like filaments, we see the opposite. So these effects are well understood, and they have to be deconvolved out of observations when performing the full analysis. So the full compilation of CFA 2 redshift survey by Hakra et al. Went well past 10,000 kilometers per second. And they noticed that there is an even larger structure they call the Great Wall, which contains in part the coma ABL 1367 cluster, or mini supercluster. And it was basically filling up the space available to their survey. Up until then, Every time Redshift survey was done, a structure was seen that was as large as it can be fit in the survey volume, which on face value of it doesn't bode well for the assumptions of homogeneity. The resolution of this came with Las Campanas Redshift survey, but before I tell you about that, let me just give you some idea how these measurements are done. In the early days, spectrographs were doing one galaxy at a time. This was a tedious work, and that's what CFA survey was. But then astronomers designed multi-object spectrographs, and they come in two varieties. First, you have to know, of course, where the galaxies are in the sky. In one type, you have a metal plate that's positioned in focal plane of the telescope, and a little opening or slit was made where each galaxy should be. Then instead of having one spectrum with a lot of blank space on each side, you have a whole lot of little short spectra with objects in the middle. The other way is to use optical fibers. Again, the fiber head is positioned to where galaxies should be, using some kind of device, usually a robotic arm. And then these fibers are grouped together to enter and slit to the spectrograph, and then the spectra are taken together. Both approaches work fairly well. And this is what really moved Redshift surveys to industrial strength of hundreds of thousands and now millions. Recall that second CFA survey was a slice in the sky, a fan-shaped slice, thin declination, long in right ascension, and they saw all these voids and filaments and stuff. Las Campanas Redshift survey did the same thing, but they did 3 slices, and they also went further out. So in their survey, they could see structures of same size up to 100 megaparsec or so that were seen by CFA Redshift survey. But they also went further, and no larger structures were seen. In other words, homogeneity does seem to apply on scales larger than hundreds of megaparsecs. And for cosmological purposes, that's perfectly good enough. 2 huge Redshift surveys really transformed this field. The first one was done by Anglo-Australian Observatory, Australian UK consortium, who used one of those robotic fiber spectrographs on 4-meter Anglo-Australian telescope in Siding Spring in Australia. They collected about 250,000 redshifts, and they did job first. They also observed a lot of quasars and so on. Their analysis really started revealing interesting new features of large-scale structure. At the same time, and continuing beyond, was the Sloan Digital Sky Survey. They used a 2.5-meter telescope in New Mexico at Apache Point Observatory, and they did both imaging survey and spectroscopic survey. They did imaging of large areas in the sky first, selected galaxies, then they used multi-fiber spectrographs to obtain redshifts of galaxies as well as quasars and so on. This was spectacularly successful. An early release of the Sloan Digital Sky Survey had something like 800,000 galaxy redshifts. But they did continue since then, and now they have of the order of 1.5 million galaxy redshifts and comparable number of velocity measurements for stars, as well as a couple 100,000 quasars. This is truly a fundamental data set on which many of the modern studies of the large-scale structure are based. So here is the redshift slice projection of the 2DF survey, and it looks sort of like Las Campanas redshift survey, only with much better resolution because they had an order of magnitude more galaxies. You can see the mesh of filaments and voids and so on, but you can also see that on scales larger than about 100 megaparsecs, we do not see super voids or super filaments or anything like that. Here is a picture showing sky coverage from the latest incarnation of Sloan Digital Sky Survey. They have these strange belts in the sky because they operate in drift scanning mode. Telescope moves in large circles in the sky as they collect the data. And then they obtain redshifts along in the same areas. This may look a little strange at first, but if you know exactly where you're pointing, you can certainly take this into account in your analysis. And here is the projection of the Sloan Sky Survey. Now again, this squishes 3D information into a plane that cuts across the sky. And we see the same qualitative features as before. a frothy kind of large-scale structure composed of filaments or walls or sheets intersecting and more or less quasi-spherical voids inside of them, sort of like sponge-like topology. There is always a trade-off of covering large area in the sky and being complete versus going deep. If you have finite amount of observing time, there are only so many galaxies you can observe, and so you can trade one for the other. These large-scale surveys that we described covered large areas, but they did not go very deep on cosmological scales. Complementary to them were surveys done over small areas in the sky, but going very deep. They're so-called pencil beam surveys because of the narrow cone. The first of those were done in 1990s, and they saw presence of large-scale structure out to high redshifts, spikes in the redshift distribution. At first, it seemed like those are periodic, but that turned out not to be the case. And now it's believed that the characteristic scale that they saw there was really due to the baryonic acoustic oscillations at scales of 100 megaparsecs, a little more. Here is the little redshift slice distribution from one of these modern surveys. This one is called DEEP, and it was done at Keck telescope, reaching out to redshift 1.5, or several times deeper than the large area surveys from before. Now, if you make a histogram of redshifts along the line of sight, you see these spikes. They correspond to intersections of clusters and filaments and walls along the line of sight. And the interesting thing is that structure keeps persisting out to the largest distances we can measure. This leads to an interesting new phenomenon called biasing, which we'll discuss in a little more detail. So here is a comparison of some of the redshift surveys. There are many ways in which you can compare redshift surveys. In this particular case, it is number of objects measured versus the volume of space that's been covered. Obviously, deeper you go, you get more volume at the expense of taking more spectra, having more objects. Now, SDSS main is the actual Sloan redshift survey. They had a few others. For one of them, they didn't really actually use spectroscopic redshifts. They used multicolor photometry to derive statistical estimates of redshifts, the so-called photo-Z survey. This turns out to work reasonably well if you have good photometry and at least several filters. And also, they can look at spectra of quasars very far away and look at absorption line clouds along the line of sight. Those are very numerous, and they provide means of probing large-scale structure out to the highest redshifts. Another way to compare them is to look at area coverage versus number density of objects that are being covered. And so again, there is a trade-off. Now in this plane, diagonal lines show the total numbers of objects. And you can see progressing first from thousands to now millions. Next time, we will talk about how we actually quantify galaxy clustering using the two-point correlation functions.